Neuvillette. I'm thrilled you've come to chat with me. Today we're diving into the mysterious world of cascading failures.
Cascading failures. That already sounds like a complex puzzle. What exactly are they, if I may ask?
Imagine a chain reaction where one minor problem can snowball into a massive breakdown. That's a cascading failure. In systems, these failures grow over time through positive feedback, leading other parts to fail one by one.
Fascinating. So it's like a domino effect within a system. How does one small failure lead to larger disruptions then?
Precisely. Consider a service with multiple replicas. If one replica fails due to overload, the others take on its load. This increases their probability of failing too, spiraling into widespread havoc.
Ah, I see. The load distribution shifts until the system can no longer handle it. You mentioned a Shakespeare service example. How does that fit in here?
The Shakespeare service example is a simple production setup. Even in a well-designed service like this, a single point of overload can start the chain reaction we discussed.
And what does this configuration typically look like? Is there a diagram or a specific arrangement?
Think of it as a web with different nodes each performing a crucial task. They all work in harmony, but a disruption, say at one node, can reverberate through the system.
Intriguing. So a well-structured design still has vulnerabilities. How do we begin addressing these cascading failures?
Great question. It begins with awareness and design methodologies. Understanding typical failure scenarios helps us engineer around those pitfalls.
Would you then say that anticipating overloads is the first step in averting such failures?
Anticipation and preparation, exactly. By identifying potential pressure points in advance, systems can be made resilient to unexpected surges or single-point failures.
The idea is quite comprehensive. But what makes the Shakespeare example particularly insightful?
The Shakespeare service illustrates a classic setup, making it easier to grasp complex dynamics. It shows how a seemingly small fault, when unaddressed, can affect a broader network.
Could you explain more on what such a configuration involves? How do the nodes interconnect?
These configurations tie together front ends, back ends, databases, all needing coordination. A hiccup at any level, if unchecked, escalates through the threads of these connections.
So in a way, each part of the service is dependent on others functioning optimally.
Absolutely. Dependencies are like strings linking everything together. Tug one string too hard, and it all rattles.
How should one ideally visualize these failure points? Are there modeling techniques involved?
Modeling is indeed key. Visualizing system load, node interactions, and failure chains helps us understand and mitigate risk.
Is there a specific methodology used to model or estimate the impact of potential failures before they occur?
Using simulations or stress tests gives us insights. By replicating failure conditions, we prepare strategies to handle actual disruptions.
That sounds quite technical. Is it all about proactive strategies then?
Proactivity is just part of it. When systems falter, reactive measures like load redistribution also play vital roles in controlling spread.
Load redistribution. Could you elaborate on how that helps during a cascading failure?
Sure, by redistributing loads evenly, we reduce stress on any single part, minimizing the risk of additional failures.
And such redistribution must be rapid, I assume, given the nature of these failures.
Fast and intelligent. Automated systems that detect failure trends and adjust load balancing dynamically are crucial.
This conversation makes cascading failures both fascinating and daunting. What more should we consider?
We've only scratched the surface. Understanding these systems' nuances and preparing for specific disruptions is an endless puzzle.
Your explanations have certainly broadened my perspective, Hu Tao. I'm eager to continue learning how these failures manifest in other sections.
Oh, there's plenty more. But I'll hold on to those stories for our next conversation. Stay curious, Neuvillette.
Hu Tao, I'm intrigued about these causes of cascading failures you mentioned. Could you delve deeper into this phenomenon of server overload?
Ah, the infamous server overload. It's like stuffing too many things into a basket until it gives out. When a server handles more requests than it can bear, it starts to buckle under pressure.
I can visualize that. What typically triggers such an overload?
Often it's a spike in incoming requests, sometimes due to another server failing, which forces the working server to take on too much at once.
And what happens once a server begins to overload? Does it affect the entire system?
Absolutely. When one server goes down from overload, others share its load, increasing their risk of failure. Soon, the whole network might crash, spreading failure like wildfire.
It's indeed like dominoes. Are there ways to design systems to avoid these overloads?
Yes, proper load testing to understand capacity limits is crucial. Picture a stress test that pushes the servers to their brink to determine their breaking point.
Stress tests sound effective. Are there any other preventive measures?
Graceful degradation is another technique. It involves serving users with simpler, less resource-heavy responses when overload occurs. Think of it as offering lemonade when you run out of oranges for juice.
A clever approach indeed. And what about managing the load more effectively? How does that work?
Load management involves balancing traffic in a way that no single server bears the brunt. Dynamic adjustments help distribute the pressure evenly among the servers.
Does this require a specific technology or software to manage effectively?
Yes, automation tools detect stress signs and rebalance traffic intelligently. They're like seasoned conductors leading an orchestra through its performance.
I'm curious about resource exhaustion. How prevalent is it in these failures?
Quite common. Imagine if a runner ran out of breath mid-race. Similarly, when servers deplete their resources, CPU memory, they can't serve requests effectively.
And what consequences arise from such exhaustion?
Elevated latency, higher error rates, and sometimes dropping of lower quality results occur. The servers slow down or even crash, spreading the exhaustion.
Are there specific resources that are more prone to exhaustion?
Resources like CPU and memory top the list, but thread starvation and file descriptor shortages also play crucial roles.
Earlier, you mentioned service unavailability. Is it a result of resource exhaustion or a different issue?
Linked but slightly different. When servers crash from exhaustion and restart, they're often bombarded by requests again and again, leading to that snowball effect of crashes.
Such repeated crashes sound daunting. How do we escape that cycle?
Thankfully, strategies like autoscaling help. By increasing capacity dynamically as the demand rises, it stops the system from constantly crashing.
What about failing gracefully? How does one decide what parts of service can degrade without significant impact?
It often involves determining which parts are absolutely essential and which are not. For example, you might skip extras like images during an overload.
A pragmatic trade-off then. I must ask, do these strategies ever introduce other issues?
Yes, sometimes they can introduce complexity or unintended feedback loops, especially if they trigger when not needed.
That makes designing such strategies a careful balancing act, doesn't it?
Exactly. It's about ensuring they work seamlessly without overshadowing the service's stability.
This conversation certainly adds layers to my understanding of system durability under stress. What other mysteries lie ahead in this domain of cascading failures?
There's still much to uncover. Let's sink our teeth further into specific testing and handling methodologies in our next chat. It's going to be quite the adventure.
Hu Tao, I'm eager to learn more about testing and managing cascading failures. How does one begin testing systems to predict these failures? It sounds complex.
Neuvillette, it's like having a crystal ball. You start by stress testing to see how your system behaves under heavy loads. Imagine discovering if your trusty wooden bridge can hold an army before they actually march across.
Fascinating metaphor. So what should engineers look for during these stress tests?
They assess at what point the system can no longer process requests effectively. Ideally, you'd want it to gracefully reject excess load, rather than crumble completely.
Graceful rejection over crumpling sounds wise. What steps should be taken if a system starts tipping into failure during testing?
That's the crux, isn't it? Recognizing signs of overload quickly. If you see excessive errors or CPU starvation, it might be a cue to start load shedding or degrade service quality strategically.
Load shedding and service degradation. Are these techniques adaptable for different scenarios?
Absolutely, they are versatile tools. For instance, You might tune them based on observed patterns like latency spikes or resource consumption.
This tuning must require a deep understanding of the system's operations. How do engineers ensure reliability while making these adjustments?
Continuous monitoring. You keep an eagle eye on metrics and adjust accordingly. Changes are often tested on small subsets first before a broader rollout.
It's clear that proactive measures are key. But what about reactive steps when failures slip through despite careful planning?
The recovery dance. You might stop health check failures, which if too aggressive can worsen outages. Sometimes simply halting these checks stabilizes the environment.
Stopping health checks, that sounds counterintuitive. How does it actually help?
Think of it as letting an athlete catch their breath. By halting checks, you prevent the system from mercilessly culling tasks that are merely recuperating.
Intriguing. Are there other reactive techniques that lend themselves to stabilization?
Restarting servers can clear snags like threads caught in a net. And if systems are truly wedged, restarting can offer a fresh start, allowing them to perform once more.
It appears every flick of the switch is carefully planned. How do you avoid making issues worse during such potential resets?
You proceed slowly and cautiously, like a fish returning to a disturbed pond. Start small, monitor effects, then escalate if needed without triggering a larger ripple.
This measured approach to resets is enlightening. How is client behavior factored into this reactive approach?
Clients are unpredictable partners in this waltz. One must ensure they don't amplify issues by retrying excessively or bypassing expected failure paths, which can complicate matters.
How does one test client behaviors effectively to anticipate these issues?
Simulating their usage patterns helps. By understanding their interactions during service disruptions, you can preemptively correct problematic behaviors.
Resourceful indeed. And what of non-critical dependencies? How should they be tested?
Those silent saboteurs. Testing ensures they don't hinder critical paths when unresponsive. Imagine if your sidekick stops to tie shoelaces mid-race. Prevent that distraction.
An amusing analogy, Hu Tao. Do these non-critical elements often pose larger hidden risks?
Often underestimated, they can consume resources like patience at a soiree, benign yet silently impactful. Testing helps ensure they remain innocuous during your system's balletic maneuvers.
Should their behavior affect the critical pathways? Are there direct steps to mitigate such risks?
Forewarned is forearmed. Ensuring isolation from critical paths through cache management or separation keeps them from waylaying your service's performance.
Cache management sounds pivotal. Does it play a role during these high-stress situations?
Indeed. Proper cache strategy ensures systems don't stutter to a stop without resources. A warm, well-fed cache keeps the gears well-oiled under pressure.
Hence the importance of robust cache management is clear. What other sudden steps might be necessary in a failure scenario?
Extreme cases call for traffic drops. It's the last resort, a tactical retreat to restore order until normalcy returns.
And in dropping traffic, how can one ensure the least impact?
Strategize with stakes in mind. Drop non-essential operations first and let the critical services receive undivided attention to remain afloat.
That sounds like strategic triage. Such discussions broaden my horizons about resilience in system architecture.
The world of cascading failures is vast, my friend, and each day brings new challenges. But with each challenge, our strategies grow stronger and wiser.
Thank you for such an enlightening discourse, Hu Tao. This builds the ever-fascinating architecture of failure management in my mind, complex yet conquerable.
I'm delighted to share, Neuvillette. Let's keep these gears turning and dive deeper into our next adventure soon.
Hu Tao, you spoke before of the Shakespeare service as a case study. How does it demonstrate these cascading failure concepts?
It's quite the gripping tale. Imagine the Shakespeare service preparing for the unexpected. A documentary airs in Japan, and suddenly everyone's flocking to the service for research at once.
So this surge in traffic pushed the system to its limits.
Exactly. The traffic surge was beyond the system's capacity, and to make matters even more dramatic, a major update was underway in the same data center.
That must have stressed the system significantly. Were there safeguards in place?
Indeed, there were. The developers had planned graceful degradation into the service. As the pressure rose, the systems stopped returning less critical data like images or maps.
Degrading gracefully seems wise, but how did the service handle unavoidable failures, like timeouts?
In those cases, the system either didn't retry or used a randomized exponential backoff for retries to avoid adding extra pressure.
Despite these measures, it sounds like some tasks did fail.
Right you are. As tasks began to fail, the number of working tasks dwindled as they were restarted, and the graphs on the service dashboard turned an alarming red.
Quite the perilous situation. How did the team restore order to the chaos?
The SREs jumped into action, temporarily adding capacity by increasing the number of tasks available for the Shakespeare job in the Asian data center.
That sounds like they were able to regain control quickly. What followed once stability was restored?
After recovering, the team wrote a post-mortem detailing events, what worked well, and identified areas for improvement to prevent this happening again.
A post-mortem sounds like a vital step for learning and preventing future failures.
Absolutely, they decided to redirect traffic using a GSLB load balancer during overloads, and turned on auto-scaling for traffic-driven task adjustment in the future.
It's crucial to be prepared for the unforeseen peaks in demand.
Right. The case shows the value of recognizing a system's breaking points and allowing some errors to prevent total collapse.
It's a delicate dance, balancing resources without overextending and risking further failures.
Exactly, and without careful assessment, even efforts to improve can backfire. Those triple retries could turn you into a meme for all the wrong reasons.
Your wit truly brings levity to a complex subject, Hu Tao. What's the final takeaway from this scenario?
In essence, prepare for the worst, learn from each hiccup, and make sure every system change aims silently to only enhance, never disrupt, the delicate dance.
Wise strategies indeed. I look forward to applying these insights to prevent potential pitfalls in my own endeavors.
There's always room for cautious optimism in technology. Together, we can keep learning and innovating.
Thank you, Hu Tao, for illuminating this topic with your usual spark and thoroughness.
Always a pleasure. Let's summon more insights next time we meet with the same enthusiasm and curiosity.
Indeed, until our next scholarly adventure. Farewell for now, my friend.